Wonderful. Hello, everyone, and welcome to the NAGT webinar series. The NAGT webinar series is a one-stop shop for increasing our community's capacity in Earth education. Webinars in our series feature novel and innovative works such as Earth education research and pedagogy, new teaching materials, and the classroom and professional experiences of people just like you. The NAGT webinar series is free and open to the public. We often get questions of, is it okay for me to invite my colleagues? Yes, it is okay. Please do. Preferred, in fact. It's really fun to have lots of people attend. And also, please feel free to use the chat box as a place for discussion, questions, and comments. Additionally, you can use the reactions tab to give like cute little emojis as feedback or thoughts. Otherwise, in terms of interactions with each other, please remember that we follow the NAGT Code of Conduct, and I'll send that in the chat if anyone needs to review it. And then on my slide here, you can see that the webinar today is bringing coding activities into your undergraduate science classroom. We also, look at that. My script is wrong. Oh, well. I'll go ahead and turn it over to Joan Marie now to go ahead and get us started on the webinar today.
Hey there, everybody. Thank you so much for coming. I'm so excited to see you all here. I had a wonderful list of people sign up, getting sort of some of the pre-registration materials set up. There's a wide variety of people, but we are all united in our dreams and hopes to educate our students and equip our students with tools to address the sort of like growing pile of geoscience data that we can all work with. And so I'm going to share this screen here now. Can you all see my screen and the PowerPoint? Yeah, all right, great. We're figuring it out slowly but surely. All right, well, then we will hide floating meeting controls. Okay, so I wanted to kind of give a rallying cry title to this, scalable and reproducible analysis for all, right? I'm very excited and passionate about the idea that if we equip our students with some of these coding, data science, and computational skills, we're going to be better off as a society because more people are going to be able to do more research about our changing Earth and how to support the populations that live there. So, as an introduction, my name is Joan Marie Del Vecchio. I use she, her pronouns, and I am PI on an Elements project from NSF. This is a cyber infrastructure grant. But really, I'm like a field scientist. I like go and dig holes in the Arctic or in Pennsylvania, thinking about past and present permafrost landscapes. But I was I was passionate about bringing more people into some of the research that you can do in the Arctic, because it turns out that most of the time it's hard to get out to the Arctic, and most of the work, the work is remote, as a rule rather than the exception. And so that inspired me to propose this project that we're in the middle of doing now, and we call it the PyCogs project, the Python Computational Geomorphology Software System. And it's a mouthful, but I wanted to get the acronym. So we're not reinventing the wheel, we're just spinning the cogs of existing data sets and software and tools to just like help people do more science. And in this case, the people are undergraduates. There's no reason that undergraduates can't be involved in some of the more cutting edge aspects of geoscience research, especially if if there's sort of remote working with data, computational data, there are lower costs associated with that kind of work. There's no sort of physical barriers. It's sort of a way to get more kinds of people involved in the geosciences. If only we can sort of flatten the steep learning curve associated with training those students. And so I'm showing you pictures here of, I've taken sort of ideas of how Arctic landscapes work, and I've equipped my undergraduate researchers that I've only been working with for a few months to work with remotely sensed data and actually learn new things about that data. And it was wonderful to see over, only a few months, students have been working with this software. Now, I got lucky because these students had taken a computer science class in the past. So they took some sort of like intro to data so they could hit the ground running. But my dream is that all geoscience undergraduates will learn these skills in their classrooms rather than just having to go to another department. We can integrate some of these lessons with the geoscience lessons that we're already teaching and that we're already really, really great at teaching. So this is my project that we're funded, and part of the funding of this project is associated with this new pilot program from the NSF, the National Discovery Cloud for Climate Research. And this is an initiative, this is a pilot that's bringing together some existing projects funded by the NSF to make sort of the ability to do climate research more accessible and easy for many people in the nation, and that includes aspects of education. And so I had a meeting with some of these PIs a few weeks ago, and there's these brilliant people, millions of dollars projects of these big supercomputers or big data centers. But when the rubber hits the road, if we don't have the training, to help people use these tools, it's going to be all for naught. And so I'd like to think that this pilot program can be reach people like you, people who are here excited about training the new generation of climate scientists, of geoscientists, and we really need to hear from you in this process. And so I'm both plugging some of the awardees that are funded on this pilot that are part of this workshop. So some of you have already requested the day pass from the Chameleon Cloud project that's providing some of the computation for today. If we get the chance, we can look at some data from the SAGE network, which is going out and collecting environmental data, but using AI to make that data transfer more efficient. And I also wanted to point out, if this is of relevance to anybody here, that one of the collaborators on this project is the Minority Serving Cyber Infrastructure Consortium, and potentially that is either your institution or an institution near you. And certainly part of this goal is making sure that everyone, every kind of institution has access to these computational resources. So it's really important for me also to make sure that nobody, it's not just the big, R1s that are in charge of this thing. It's that everybody has a chance to engage in these computational and cyber infrastructure tools. All right. So that was all a mouthful. That's all the big introduction, but I welcome you now to give me a little bit of a taste of who you are. So if I drop this into the chat, that is a Slido poll where I'm going to ask you a little bit about what kind of institution in which you will be working with students, just so that I can get a chance to see who's in the room and what the interests are. I will share my screen here. Maybe I will share my screen. Maybe I won't. Maybe I will just tell you so as not to risk having the house of cards of the dual monitors and screen sharing fall down. Okay, so here today, many of you, majority of you are from four-year colleges. A healthy portion of you are from two-year colleges. Some of you are from government or federal funding sources that are working with students, and I saw that in some of the comments. And so I want to not accidentally talk about classrooms too much, but just general training of undergraduates. And then maybe in the other, if you feel comfortable, you can drop in the chat the sort of institution you're with, just so that I get a sense of who's here. All right, we have three-fourths of us participating. That's pretty good. Looks like many, 2/3 of you are from four-year colleges here. All right, great. One or two last votes. I feel like I'm in front of my class. Like, all right, finish up collecting the quiz. All right, great. So I'm going to move on to the next question here. And this next question, if you are on the same URL, hopefully it just shows up. I just want to know, how comfortable are you with coding right now? Have you ever used it? Have you used it a few times? Some of you actually said that you've used Python in maybe your own research, but you've never brought it into your teaching. And perhaps, yeah, most intimidatingly, some of you have actually used it in your classroom. And In which case, maybe, you know, feel free to chime in with your best practices, because I've only been doing this for so long myself too. Cool, okay. Let's get a few more answers. We're just over halfway. I would say about half of you right now have used it a few times. Equal parts otherwise have never used and have used it in the past. And yeah, like I said, some of you have in fact used it in your research and teaching. There will be, I think, when we kind of have some hands-on activities, you may find that if you're more comfortable, you can step up to some of the more challenging activities, but there are very much novice activities as well. All right, great. We've got our 3/4, whatever that is. That's majority. I don't know if that means we can pass laws in Congress or not, but I would say that, yeah, half of you have used Python a little bit, maybe a third of you have never used it, and then other folks have used it a little bit in the past, maybe in some of your research and some of your teaching. Awesome. Well, thank you very much. I have one last question for you, and this is going to be a word cloud. So I am going to figure out how to share this screen. I don't, might be a disaster. Let's find out here. So I'm going to deactivate this poll. And then my final question for you is, what are the barriers that currently stop or limit you from teaching coding in your classes? And this can be anything. And I'm, you know, I'm not kidding when I say this is valuable data. Like, I want to pass this on to the, you know, other NSF project PIs, the program officers. Like, what do you people need? You know, what do the people out there need if we're really going to train the next generation of geoscientists? Like, what do we need to equip the educators with? And I'll give people a couple of minutes here, and then maybe in the process, I am screen sharing. All right. I'm going to do, here we go. Let's do this. Screen share 1. We've got our word cloud. All right. I am loving these examples here. This is great. I think time is an incredible constraint, right? You are busy people. You might be teaching 2, 3, 4 classes a semester. You're not gonna, you know, you've got your groove. You've got your classes prepped. Oh my gosh, I'm so excited when I have my classes prepped. Oh my gosh, it's gonna be so, I'm just gonna cruise, right? Like, why, you know, how are you gonna learn something new when we have time to learn something new? The examples, okay, great. It's like, oh, like there's nothing out there for me, or maybe I don't know where to find them. And then, yeah, not knowing how to code. Like, I've never done this before. How on earth am I going to teach my students if I myself don't know? Very valid, super valid. Yeah, definitely, like, you know, time to revise the curriculum. You know, there's this sort of like, I know my students want it, but I don't have the capacity to both learn something new, change the curriculum, provide the support for the students. Yes. And all of those are big challenges. And I'm not going to say that by the end of this, we're going to come away with an answer, but at the very least, I think we can come up maybe as a group or as a community with some insights or strategies that we might use to tackle some of these. Let's see. Yeah, all of these are really good. All right. So we've had our 30 so people vote. Any last thoughts, last data that I'm going to collect? And then I'm literally going to pass this word cloud over to the cyber infrastructure program officers who are like, hey, like, if you're doing a webinar, let us know. And I was like, oh, I'll let you know. I'll let you know what the community needs, you know, from the NSF, from folks giving out the money. So have your voice heard. And of course, there'll be time in this activity later. We'll have a chat. We'll have some feedback. Okay. All right. Well, thank you so much. I'm gonna pause us for now so that we can keep on trucking, and hopefully you see my screen still. Great. Okay, I'm gonna hide my floating meeting controls. All right, so why implement Python in your classroom? So one of the big things I'm excited about is I really want your students' research and career prospects to be supercharged. And so, we're not just thinking about students who might go on to grad school, we're thinking about industry, we're thinking about people whose, managers whose minds will be blown when your students work with data in such an efficient way. I'm hopeful that people can come out of this with employable skills, desirable skills. The fact of the matter is that with the advent of all of these great computers and all of these great, semiconductors, microchips, we're collecting so much more data about Earth these days that both the volume and the nature of this data means that, and you may have noticed this, if you try to download a huge data set or you try to bring in a big, map on ArcMap or something, your little desktop computer might struggle to do these things. And yet that data is out there, it's waiting to be analyzed. We just need some specialized knowledge to work with it. Something that I'm super passionate about is that, by having these coding skills, we're sort of democratizing access to Earth and climate data. And I hope that that leads to, historically excluded groups from the geosciences, folks who maybe didn't have, coming from institutions who don't have the sort of monetary resources to go out and collect the field data, go out and collect the very technical data, all of this data is available. And as long as you have, an internet connection and a little bit of coding knowledge, you can do just as good cutting edge research and sort of investigation about Earth. And maybe, that will lead to more people addressing and solving some of our climate issues. And finally, and the thing that I'm going to sort of dwell on for another slide or two, Python and all sorts of like coding methods facilitate scalable and reproducible scientific research. So what do I mean by scalable and reproducible? These are sort of buzzwordy here, aren't they? So by scalable, I mean that it doesn't take any extra human effort or very, very minimal extra human effort to do the analysis on a larger and larger data set. The way that I sort of explain this to people is that your workflow can grow with your imagination, right? If you've got a student who's super curious and they look at one little data set and they come up with an interesting answer, if they're doing things by hand, they might not be interested in doing the second or third or fourth or fifth data set if it takes them a really long time. If they've written a code that churns through that data automatically, all of a sudden they can answer 5 times as many questions, in the same amount of time. By reproducible, I mean anyone can use your input data to generate your results. And I think this is sort of a sort of hidden benefit to working with undergrads. And when you say, oh, undergraduates aren't, publishing, peer-reviewed paper, why do I care about reproducibility? I think one of the things that helps is that it minimizes the opportunity for human error. So if you've, used coding to do your calculations instead of punching in on a calculator or doing something by hand in Excel, it helps, I think, your students understand why they make the mistakes that they do and correct those. It also means that your students, you can go from start to finish, going from raw data to your plot in sort of a single script or a notebook. It means that you're documenting everything from data acquisition to plotting results, which means that you can understand what your students are doing when they show you a plot and you ask them, what does this mean? What is this data? We can all look together at the code to understand it. These also sort of go hand in hand with fair data principles. And so fair data are findable, accessible, interoperable, and reusable. And it is fair data that also fuels this like geoscience revolution and allows people like our students to use these data. So if you are someone who is producing data, keep these sort of fair principles in mind, because a student down the road may thank you when they can use that data. So what's stopping us, right? And like you said, and I saw examples was a big word. And here's my slide in response to the example word cloud. So there are, in fact, many resources online for folks who are actually comfortable with Python and want to sort of use them in maybe advanced classes, maybe graduate students, maybe their own research. And if you're one of these people here who has used Python in their research but are interested in teaching, I would encourage you to check out some of these resources. NASA has a cookbook, so it's like a bunch of example scripts. Project Pythia is another resource for, more complex computational processes. Other people have published their class textbooks online as Jupyter notebooks. Ryan Abernathy at Lamont has done this, and I've sort of borrowed some of his code snippets here and there. But that's all the way up there. But when we're talking about accessing novices, I'm not using Circ here as I'm just saying that this is the state of the art right now, is that many people in the earth sciences have used things like MATLAB, Excel, and ArcGIS historically. We haven't had the time to, revamp our curricula. And so what it means is that the scalable and reproducible, the open source versions of a lot of these activities have had relatively less love when it comes to, people producing examples to be used in the classroom. So one of my dreams is that as part of this NDCC pilot, we will create some of these examples that are meant for novices, but still really interesting, doing, open source, scalable, and reproducible science that bridges the gap between the experts and the novices. So I just want to throw, I have a video here to show you a little example of what it looks like when I have implemented this in my classroom. So one of the questions I have asked is, okay, in the face of climate change, are we seeing floods that are bigger happen more frequently, as time goes on? And so that data is super out there. The USGS has, historical gauge data across the nation. And so theoretically, right, if you are doing this, you're going to go to their website, you're going to try to download the data from the USGS website. You're going to scroll through this sort of mess of nasty data. You're going to copy it into Excel, hope that it works. Okay, we're going to have to format the data to make it in the format that we want it to be in. We're going to manually check, there's a cell that's gotten messed up a little bit. Guess I have to type that in and fix it. You've seen this, right? And then, if this is your students, they're maybe getting frustrated because they're clicking and dragging, they're mistyping, they don't know what buttons to click, to get Excel to do the thing that it wants it to do. And when you go to make a plot in Excel, you want to make your axes a certain way. Maybe it's really difficult to do that. And I'll fast forward here. You don't have to see me doing crazy Excel stuff here. So, your plotting is limited. You maybe have to, adjust things by hands to get exactly what you want. And maybe it's hard to even answer the question that you want to answer with this data. It's hard to plot 3 different kinds of data in Excel at a time. We can't really answer the question of have floods been getting bigger over time super easily. It's taken us, 3 minutes to get to this part. And I was very practiced in this. I did this a million times. And so this is the fastest, this is my world record of 3 minutes. So consider the alternative where we have, a Python notebook where we use, and this is an example that we can go over today in this webinar, we just need the number, the gauge number, the gauge name basically. And we can ask the USGS servers to serve us that same data. If we're thinking algorithmically, if we're thinking that, yes, their servers store this data in the same kind of way, and we're going to do the same task over and over again, we can then get plots from the USGS very quickly over and over again. And so in this video here, I've showed you that it's taken, 30 seconds to get 2 different stream gauges worth of peak discharge trends. Yeah, and it sort of runs, and all you have to do is plug in the gauge number and you get the answer, right? This is the dream, right? So if we could ask students, hey, go out and look at that data and answer this question about this Earth system, that they can be at this point. But of course, we have to train them to get there. But once they learn this skill, then it's wow, they've solved this puzzle. They've learned to think algorithmically, and all of a sudden they're going to be, collecting more data and doing more analyses than would have been possible if they were doing things by hand. So I'm just gonna like quickly show, or like this is a quick representation of how I've used this in my class for the people who maybe are comfortable with Python and are interested in bringing it into their class. So my personal strategy has been to pair a learning objective in my class. And so I've been teaching a surface processes class. So I have a geomorphology learning objective that I pair with a software learning objective. And we try to do both at the same time. And, so far, so good. I would say that, some students gravitate more towards the, content learning objective. Some students get into the software. But each activity sort of has two things that I try to teach. I try to teach a fairly simple geomorphic concept and a fairly simple software objective. And so I have packaged some of these activities as sort of self-contained notebooks, and we're going to see what notebooks look like in a little bit. And so if you're somebody who feels good about this, I encourage you to check out my personal GitHub or the PyCog's GitHub, where you can see some of these notebooks in action. And I just want to put it out there that I had my students tell me before and after using these notebooks how comfortable they felt with some of these activities. And it turns out that for the, software skills and the data skills that I was trying to teach, overall, over just the course of a 10-week term, I took students from being relatively uncomfortable to relatively comfortable working with these data and working with these sort of computational tools. And so it seems like it worked. And I had some really endearing phrases in my course reviews. I had the student say, I felt like I was doing actual real life science, which is great and terrifying, because what have you been doing in your other science classes, right? I've had students this year, as I've been teaching this, more than one has said, oh, I'm feeling very STEMmy. And I'm like, okay, great. You're in a geology class. It better be STEMmy, but it's empowering them. They're feeling like, wow, this is cool that I'm doing this. I'm like making these maps. I'm writing these codes. I'm making these plots. It's empowering for them. They're learning things. They're being challenged, but they're learning. So that's all the whys. We're going to talk about the hows. And we're going to sort of take a deep breath, because we're going to start to learn new things here. And some of you, novices, thank you again for being here, for registering. You said that you don't have a lot of time. It's that you have to take time out of your schedule to prep new material. So thank you so much for being here. I hope I can do you a little bit of justice by showing you how to go about doing these things. If you're more of an expert, some of this might be review to you. So, just hang tight for a little bit. I'm putting these two images here, these two examples of existing material that works really well. So on the left here, you can check out Software Carpentry. This is an organization that it seems to be the very standard, the go-to for sort of earth scientists who are like, how do we teach people the very basics of coding and software? This is always the first step, as far as I can tell, for some of the more, for NASA, for, some of the other organizations that I've been a part of. This is where they send the novices. And so you can check that out to supplement what you learn here. On the right is very earth science specific guides. So CU Boulder has an excellent suite of free online courses, tutorials, and tools in their Earth Lab. And so this is your examples. This is your efficient use of your time. If you check this website out, you will see that there are many examples with lots of text, lots of explanatory text, lots of examples of how to use, data science for Earth applications, but then also just, general Python, general scientific plotting. It's really great. Like I said, I've sort of, borrowed here and there from some of these to build my materials. But how do we get there in the first place? Like, how do you do Python? I think I saw in, one of the big word clouds was like, how do you install Python? How do you use Python? And that is a very good question. So I'm going to do my very best to make it maybe as quick and simple as possible here. So one option, and this is maybe something the people who are like, how do I install it? When you're saying okay, I'm going to install Python. So that's if you want to have the software on your personal computer. And this is, many people's introduction to Python. And this was definitely how it was done, over the past few years. So this is, your laptop. This picture is like on your laptop. You are going to go to, Miniconda or Anaconda Navigator. You are going to hit the, you're going to click an install button. Things are going to whirl through. Your computer will then have Python and an environment or package manager in the form of this Conda. I'll tell you about that. And then from there, you will load up Jupyter as sort of the platform with which you will access Jupyter notebooks. So Python is installed on your computer. You're running Python. You ask Python to basically load up a program called Jupyter, and then there will be notebook files that you can then open in this sort of like Jupyter interface. So that's one way. Increasingly, though, institutions like schools, so some of you maybe are at R1s or R2s that have the resources to maybe host either a cluster of computers physically on campus, or your institution has what's called a Jupyter hub. And in this way, all you're doing is using your personal computer as basically the portal through which you are going to then access Python as it exists on another computer. So that might be the high performance computing cluster, the server racks with the lights flashing on and off that you've, maybe never paid attention to as you walk past, but like those might be running Python, and your computer, your dinky little laptop, can embrace those big computers and the Python that's running on them. So that's one way. You can SSH, you can use a secure shell to access the Python on those notebooks or on those servers, or your school is running a Jupyter hub that you then you call it like for, wnm.jupyterhub.edu or whatever, it's something that is maintained by your school. And that also has a Python and an environment sort of on it. So all you're just spinning it right up. Jupyter Notebook starts right away. This will look like what we're going to do today, if we're accessing Binder or Chameleon Cloud. You're just using your computer to basically log on to a platform that does not exist in your computer. And then finally, we have these cloud services. And so if you've wondered what is the cloud, what's happening in the cloud, basically, it's just a server rack that lives in the desert in Arizona rather than on your campus or, at your research facility, right? You're using your computer to ask, Amazon or Google to run Python for you. And the only difference here is that this is, there's a million servers rather than, the 5 computers maybe at your institution. But once again, a lot of the installing Python is under the hood here. You log right on and you're using Python right away. So those are the kinds of environments that you can avoid the how do you install Python question if you have those resources available to you. And a lot of those resources are actually free, or you just need to, sign up and ask, the NSF Access computer cluster to give you some access, and you're good to go. Okay, so that was a lot. I've filled your brains a little bit. I'm going to keep going into some of that, but I want to take a moment. Check in. Can I answer any questions? You want to chat? You can unmute. I can help. All right. Oh, we got chat. All good. Thank you. Heck yeah. All right. We're cruising. We're doing it. All right. Let's, nobody's going to unmute. Oh, is there questions? Okay. Let's keep going. Let's keep learning. All right. Awesome. We're going to hide those floating meeting controls. Okay. So here we go. How to implement Python in your classroom. We're going to install Python. What does that mean if you install Python? I found this very helpful graphic online, and what it's showing is that, so Conda is a package manager. It's an environment manager. And what I mean by that is that basically anytime you're running Python, you're running it on a tiny little like virtual machine inside your computer or on the server somewhere. And on that little virtual machine, you want to add the packages that do the things you want to do. So Python is the language And then Conda is the manager of those packages and the environments that you can build. So if you right now, if you want to, if you're in the background, you're like, I want to install Python, you can go Google right now, install Miniconda or install Anaconda. And if you click those install buttons, you will get a copy of Python as well as a copy of Conda, which is this package manager. It depends. I would say that like Anaconda Navigator is kind of nice. It's a little more of a graphical user interface. If you're new to this, there's like buttons that you can press. Miniconda is more of the command line. And so if like you are somewhat intimidated to talk to a computer by typing, that's maybe not your bag. So you want to go, install Anaconda. So once you install those things, then on your personal computer, you can do whatever you want with Python. And what that looks like is installing packages to do these specialized tasks. And so maybe you're familiar with R. R has libraries. MATLAB has both community add-ons as well as like toolboxes that you install. These are sort of analogous. So what this looks like in practice is once you install Miniconda or Anaconda, you can open up the Anaconda prompt, or if you're an Anaconda Navigator, you can like navigate to the environment and you'll see this base environment. And this is like, okay, this is, the out of the box, like basic base environment. And into that basic base environment, we can either install packages right away, or we can create a new environment. And so in this example, this person is creating MyEnv, an environment, and they're installing a specific version of Python. So you can create as many of these little virtual machines, these little environments as you want, depending on the specialized scientific task that you're going to do. Once you've created that environment, you then install, you use either the command line or you use Anaconda Navigator to click and drag around, and you want to install these packages. And so I am installing, in this example here, a package called NumPy or NumPy, and this does all the math. Turns out that Python can do very rudimentary math on its own, but if you want to do other things, you're going to want to install NumPy. And once you've installed NumPy, you then can bring it into your script by importing it. And once you have imported the package that you're interested in using, you can do all sorts of things. And I grabbed this just as an example from one of the notebooks today that we're going to see. So Python, language, Conda, package manager, environment manager. You use Conda to sort of navigate around your little virtual machines. And into those virtual machines, you are going to stuff all these fun packages that other people have created to do all these nice specialized tasks. So as the last thing I'll say is that if you are not installing it on your own machine, but instead you're using, say, Google Colab, or you're using Jupyter Hub, or you use some of the examples from today, all of that other stuff has been done under the hood for you. The only thing you're going to have to worry about is importing the packages that you need. So once again, this is sort of my, depending on how granular you want to get into this with your students, you might want to stuff a lot of that under the hood. That's been my approach, honestly. Sort of, I haven't had students install things in person. I've had students access Jupyter Hubs or other sort of like servers where they don't have to worry about managing environments. Okay, another break. This is questions right now. Okay, I love your description of cloud computing. Thanks, Freddie. Other comments, other questions? No? Okay. All right, I'll keep trucking. That's fine. Oh, here we go. We have a chat. Oh, okay, great, helpful. Yay. Okay. So this is a lot of slide, but I wanted to kind of put this all up here. And so this is like, you now ask yourself, okay, my institution, my situation, where am I going to put my Python installation so that me and my students can run our notebooks? And I've kind of ordered them what I think would be like the least amount of friction in a classroom, just from my experience. And so the top one here is that institutional. And I recognize that like not everybody's coming from an institution that might be able to support a Jupyter Hub. You're paying some amount of money, or you're paying IT folks to maintain this. But so many institutions do have these Jupyter Hubs. More often than not, I'll ask someone if their institution has it, and even if they didn't know it, they'll search, and indeed, somebody's already paying for it. Maybe the computer science department is using it to say, hey, computer science, actually geology wants to give this a role. And so, check if your institution has a Jupyter Hub, and or reach out to your IT or research computing department and see if they have ideas. Usually those people actually have very strong opinions about where students should be doing their Python. They might, have specific recommendations for your institution and for your students. I found that most institutions, research computing or IT folks are actually really interested in talking about easing access, shortening the time to science for the students on campus. A second option are some of the things we're going to do today, or some of the things that I've sort of provided as an option for access. So, the National Science Foundation, NASA, other individuals pay institutions to run servers, run cloud computing software, environments for people to access, for researchers to access. Literally NSF Access, I don't know what it stands for, but it is literally like, hey, come use our computers. And these were some of the people who were also involved with the climate cloud. And they said, please send people our way. Like if their institution does not have the computing resources, like we want to make that happen to them. So here's just like a quick list of, people that you can Google after this to see if they can hook you up with some computing time or resources. Another option we're going to do today is Binder. So mybinder.org is community supported. It's by donations. And you can launch any GitHub repository on this binder. You might find later when we go to run it, it's a little slow. It may be down. That's the problem with something that's run by, donations. So be aware of that if you're going to use that for a classroom or something. And then Google Colab, Google has a platform that makes it actually really easy to work with notebooks. They actually give you pretty good computing resources and data time. You just need a Google login, and you may or may not have philosophical reasons to do that or not do that. And then finally, if push comes to shove, yes, maybe you try to get your students to install Anaconda on their computers, or maybe some lab computers that might be, if all else fails. All right, I see some things in the chat. I'm just going to check. Do you need to have, okay, great. These are some good questions. Okay, so the first question from Amber, it says, do you need to have a Unix-based machine? No, you don't. And so Anaconda and Miniconda will run on Windows. There's just, there are ever so slightly small differences. There's like forward slashes versus backslashes, but totally you can install Miniconda, Anaconda on PC. Mac is just sort of like, Mac is sort of under the hood running something that looks a little more like the Unix. And so it's like slightly easier, but I don't know, I'm Windows gang, and like, okay, maybe I sometimes run like Linux under my Windows, but like I'm doing things on Windows, I'm surviving, it's fine. So there's a set of instructions to follow to do the installation. This is a good question, Laura. So I haven't included the instructions on this presentation, but if you go to like install Miniconda or install Anaconda Navigator, those web pages will take you through that installation. Okay, third-party platforms needing a grant. How portable are these things to students? So this is a good question. So this goes through the sort of like middle and third-party platforms. So Binder, Google Colab, no cost whatsoever, or at least like the sort of basic computing has no cost. Google Colab, as long as you have a Google account, you can do honestly quite a bit of computing. My understanding is that a lot of these NSF funded things, the NSF's Access National Data Platform, the Texas Advanced Computing Center, all of these things might require you to have a login, and you might have to like kind of tell the government what it is that you're doing. And so there's, besides the sort of like privacy concerns there, that's going to just like depend from platform to platform if someone needs you to have a grant, or if there's just sort of like a pool of resources for more of the like teaching environments. My understanding is that people are really interested in getting teachers to use these resources. And then Susan asks, what is GitHub? Okay, great question. And I have a slide on this later. So GitHub is a website that is a place for people to post publicly their repositories for code. and it makes it easier for you to either download or copy or work with other people's code. You then work on it on your own sort of account, and yet you still maintain some of those ties to the original software. So what it does is it sort of leaves like a little bit of, it can leave like little breadcrumbs where like you can actually link your version of the code to the like big code, and you can like get updates. I like GitHub because you can use it and go to a repository and go to the issues, and you can actually ask a question that gets posted to the community. And I'm going to actually recommend that people do that at the end here. If you ever have questions, especially for my stuff that we're going to work with, if you get stuck, instead of an email, try a GitHub issue, because then other people might have that question. And we'll all get to see what the problem is, and I will sort of publicly try to solve your problem, which might help tons of people at the end. Okay. I want to answer. Okay, some of these people are good. Okay, Zach's 2-year college, biggest challenge, don't have their own laptops. That's a great question. So I think that one thing that you will be interested in are the sort of like URL web-based platforms. So for example, I've had students run their notebooks on like there's technically nothing stopping you from running it on like a smartphone. Like it could run on a smartphone, it could run on a tablet. If you have a URL, you could hop on any computer connected to the internet to do these activities. And that's why I'm sort of like, if your school has a Jupyter Hub, or if there's a way to get access to that, I think that is the platform that has the least amount of friction. So, oh my gosh. Okay, so there are still a lot of questions, but I want us to do the examples. So I am going to I'm going to keep answering questions, but I am going to give everybody the opportunity in this remaining time. Okay, so I've just sent you links to the 2 different ways that you might access some of the activities that I'm going to give you. So on the Chameleon platform, if I have already approved your day pass, go right ahead. If you didn't ask for the day pass, I can go like approve them, or just jump on the binder link, because that will have already been compiled. You don't need any specific access. You can start playing around right there. And then the GitHub repository is to see where this content lives. And it's on my GitHub. It's basically on like a public website that you can just like look at whenever. You can hit the download button and you can run it on your own machine as well. I am going to answer, I'm going to let everybody do that. I'm going to answer Juan's question. Is there a public repository of geosciences? Yes. Okay. So that was, well, first off, I'm hoping that my project at the end will have those resources for you. Yeah, there's not like a central great place other than those these cookbooks that I was showing earlier. Let me go back to that slide, because it's been a while. So, but you might still want to Google these things. Okay, so these cookbooks over here on the left. So these are earth science examples. And they're great examples. They're just kind of advanced. They presuppose quite a bit of knowledge about coding and about data. And so it's true that there aren't enough of these example data. You can check those things out, but if you're a novice, they're only going to be so helpful. So on my GitHub repository, I have the examples that I've created for my class. You're welcome to check those out. GitHub is another place where you might actually find other geoscientists who have put notebooks out into the world because they taught a class or they have examples. So that's another way that you might find material is on GitHub itself. Okay, so all these people, okay, all right, no more outstanding questions. So I was gonna share my screen and like do examples, but it's like it's already at the 49. So maybe I will just let people do that, and in the background I will put the slide that I was going to show after. And people are like working, maybe people are Any questions for me? Not sure what to do once we get to those pages. Okay, yes. Okay, so then maybe I will share my screen. Okay, all right. So on the left, and if I do, for example, if I get to, let me go to chat. So over on the left will be the notebooks that you can look with. I've just lost, oh, here's my chat. I'm looking at it. Okay. So if I go to Chameleon Cloud, I can show you what it looks like on Chameleon. Okay. Da, 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 da. So you are hopefully going to see this screen. And hopefully folks both on Binder and Chameleon see something like this. Okay, so over here is this like really nastily named file over here. Are we seeing my screen? Yeah, okay, cool. All right, so all of these are notebooks over here on the side. So this is good because they're not just random. So Python and NumPy is like the super basic notebook. This is if you are a novice and you want to learn, and this is where we are going to both read text and execute code. You execute code by either hitting the run button or shift enter. And if this material wasn't commented out, something would happen, but I can show you what happens. If I do shift enter and then I print G, boom, I've done it. I've run Python, I've executed a thing. I am seeing some things. How do you get to this screen? Through Chameleon. I followed the Chameleon link and it brought me here right away, Laura. If you are running into an error, you can send that to me. Otherwise, you can, let me see if I can do. So otherwise, if you like back out, you can launch this activity on Chameleon and hopefully it loads up right away. And it's under experiment trophy. And then it's cool. All right. Thanks, Susan. Thank you for letting me know. Okay. Yes. Okay. Great. Cool. People are launching. People are having a good time. Okay. So what do we do when we're here? So this is sort of your playground time. Take a couple of minutes to explore. So for example, in this Python NumPy notebook, I can go through and just basically, in order, execute cells to see what happens. So for example, okay, I've created a list of numbers here, and now I've stored it as temperatures. And so this is a notebook demonstrating sort of the super basic parts of Python. We haven't even brought in any packages here. We're just using pure Python. And, turns out that pure Python can do plenty. We don't even need to bring in NumPy to do basic addition. Turns out basic Python can do that. But if we want to start to do anything tricky, so for example, down here, we're going to use NumPy to do some slightly trickier things, like make a list of numbers that are from 1 to 6 that are spaced every 0.5 away, things like that. We're learning about the way that data is stored. We're learning about how we can abbreviate. NumPy is NP, so you don't have to type NumPy every time. And then I have, down here at the very end, I've included something, a very simple example, but something that you might run across. Let's say you have some data. Maybe you're even working with elevation data, so it's 2-dimensional. And maybe you have like a no data point in that data. So you have this not a number, this it's not 0, but it's not nothing. And so something that, we can do with Python is try to ask it, well, what's the maximum elevation? And suddenly we've got this error here, this won't work because Python doesn't know how to handle this missing data. But NumPy, if we work with NumPy, we can ask NumPy. So the max function actually gets a little confused. It says, actually, there's a not a number in there. So I don't really know how to handle that. So it turns out that, there's a special function called nan-max where we say, okay, considering that there might be no datas, what's the maximum? Boom, we get our right answer. We get our 300. So this is just, one example of, say, you get some really messy data. A student collects some messy data somehow. You can use things like Python to mess around with it. So there are there's 4 other example notebooks in here. I would say that the order goes like Python, pandas. The stream gauge example is one that I use in my class. And then the SAGE data example is one that uses some of that like internet connected data to showcase some of the other cool things that people on the Climate Cloud project are up to. I recognize we're towards the end of the hour here, so I want to show our last little bits here. So GitHub, okay. We were talking about GitHub. What's GitHub? GitHub is a place where code lives publicly, and this is where I say, this is where instead of sending an email, if you go to GitHub and say new issue on a piece of software that you found on GitHub that doesn't work, then the public knows that you have a problem here and like you need to, fix the software rather than sending an email that may or may not get answered by someone in a timely fashion. So that's that. What an incredible talk. Okay. Yeah. Oh my gosh, we're at the end of time here. Oh boy. All right. Dorothy Barretts, who may be in the audience, tried this and she has some really good ideas. She had her students, work for 10, 15 minutes by themselves, 5 minutes together, 10, 15 minutes themselves, 5 minutes together. She started classes with warm-ups to remind people of what they've done in the past. We did work together ahead of time. And so, her advice was to find a group of peer to work with for implementing this so that you can all work together. She also says that, yeah, some people will really love it. Some people will get really frustrated. Some people will like the puzzles, some people won't. And just like preparing yourself to see the range of experiences that you might see with students. I want to leave us. I do want for people who can hang out and type me things like, what do you need to succeed? You've had this webinar. I've shouted at you now for 57 minutes, but like, what are you going to do after this? Should I make short videos like Dorothy recommended, 2 to 5 minutes to like gain a skill? Do you need the knowledge that I'm still sort of Googling things? I have nothing memorized. Like I'm Googling everything all the time. Do you need more beginner lessons with geoscience? Do you need easy access to Python environments? Do you need to go talk to that research computing or IT people to help you get access to Python? Do you need a community for learning and support for implementing these things? And, if you have the ability, please share with the group or send me an email or message privately. All of these, I want to collect data on what it is that you want and need with the NSF logo there saying that like, I'll do my best to pass these messages on to the program officers. I'm seeing people drop things in the chat. I'm so excited. I'm just going to leave you on this screen. Thank you so much. Congratulate yourselves for trying something new and challenging today. You've hung with it. You've tried things. You've asked good questions. Please be in touch. Use my GitHub repo to bring up issues so that everybody can see your question, or, I'm happy to have something emailed to me. I'm seeing lots of things, lots of questions. Thank you so much. I'm going to try to answer things. Useful information, synchronous learning, yes to everything. Somebody saw me talking about ChatGPT. It's kind of true. Like if you are a coding novice and you can ask ChatGPT, like, write me this code and why this works. Hate to say it, it's very good. It's pretty resourceful. If you are someone who wants to learn, I'm not going to say don't use it, but like, it's pretty good. Need beginners lessons. Will this work under ArcGIS online notebook environment? Wow. I don't actually know because I don't use ArcGIS. I use all of my GIS in Python because I'm too cheap to learn to buy ArcGIS and learn new Arc. Relatively quick and cheap, requires a login. Yes. So definitely I'm interested in reducing some of the barriers to getting people signed up and using some of these resources. So thank you all for the comments and feedback and information. Even just getting this webinar set up, we all learned what I need to do in order to bring geoscience and to coding to the geoscientists. All right, I'm at my hour. Ashley, there you go.
Yes, thank you, Jean-Marie. This was really wonderful and really helpful and useful, and it sounds like many people are taking wonderful things away. And I just want to close us out here. Thank you again, Jean-Marie, for a wonderful webinar. You'll be able to find resources that Jean-Marie linked to, and also the recording from the webinar on the webinar page. It just might take a few days because we do get the webinars professionally captioned. And our next webinar is Teaching with Investigation and Design, an opportunity to transform your introductory undergraduate science classroom, which is next Monday, 12 p.m. PT, 1 p.m. MT, 2 p.m. CT, 3 p.m. ET. We also have an end of webinar evaluation for you all to fill out just to give us a little bit of feedback. Also, you'll be able to get to the I see what's happening. There we go. I sent that in the chat right now. And that's also how you'll be able to get to the certificate of attendance. Thank you again, everyone, for joining us today. Thank you to Jean-Marie for a wonderful webinar. Bye, everyone.
Thank you all so much again. Wonderful questions.
Thank you so much. That was excellent. So much energy. Very great. Thank you.